second quantity that's very closely related to momentum, and we'll see just how closely it's related to momentum in a few minutes, is the impulse. So we can talk about the impulse exerted on an object by some force. So when a force acts on an object, the impulse that force delivers to the object depends on the magnitude and direction of the force and the time interval during which it acts on the object. When we took our force and integrated over displacements, that gave us a work term. So we're going to use J as the letter symbolizing the impulse, and we can calculate what the impulse is by taking the integral over some time interval of whatever the force is integrated over infinitesimal chunks of time. So again, there's some fundamentally important things this equation is trying to tell us. The first one is, of course, that the impulse is a vector quantity. J, as a vector, has as many components as there are relevant dimensions for the problem. So if there's a two-dimensional problem, then you've got an x component for the impulse vector and a y component for the impulse vector. And the x component of the impulse depends on the x component of the force. The y component of the impulse depends on the y component of the force. Second is that the impulse delivered to an object by an individual force points in the same direction as the force. Now this gets a little bit trickier if your force varies in terms of its direction over that time interval, and we'll talk about a way to deal with that in a minute. 3. The magnitude of the impulse depends on how strong the force is and how long it acts on the object. So obviously if you have a really large force, that's one way to have a really large impulse. But you can have a moderately sized force but have it act over a really long time and still get a large impulse. So we'll also deal with situations where we might have moderately sized forces, but only let them act over a very short time interval, and in that case we can treat their impulse as effectively negligible. Last, of course, is that impulse has units of force times time. So we can write the units of impulse as Newton seconds, but another way to write a Newton second is kilogram meters per second, and that unit should look familiar because it's the units of momentum. So part of what this last little bit in terms of thinking about units is hinting at is just how intimately related impulse and momentum are. They have the same unit. So if that force is constant, then obviously I can pull it out of the integral. I'm left with an integral over a time interval of dt, which just gives me delta t. Because again, this is a vector quantity, I have a vector equation for each dimension that's relevant. And so here I've plotted what one of those relevant dimensions would look like if I have a constant force. And so you'll notice that in this case, the impulse here is just the area under the curve, and if I have a constant force, that force value doesn't change, and so this just means I have the area inside this rectangle that's bound on the right and the left by the initial and final time, the time interval that I'm interested in. Well, what if I have a complicated force? So if F isn't constant, and so it varies in magnitude, so when I have a complicated force, one thing I can do to again sort of avoid dealing with the complicated calculus that dealing with a force like this requires is to say, well, I get the same answer for the impulse by thinking about the average force. And so the average force here is defined to be what is the force that when you think of it as a constant force gives you the same area under the curve that you would get calculated the area under the curve for this complicated structure. That average force then gives us the same impulse, it just does it in a much simpler way. So what this means then is that the average force can be thought of as the constant force that would give the same impulse over the time interval as the time varying force does. So this is one of the strategies that we will often use, is even though we may have a force that's incredibly complicated, I may not be interested in dealing with all that complication and am willing to deal with, well, on average what's going on that's going to give me the same impulse but makes the math much simpler. So what if there are multiple forces acting on an object? Well, of course, I can calculate the net impulse by summing up all the individual impulses that act on the object. So if I have multiple forces, each of those forces, I can calculate the impulse due to each force. If I add those up, I'll get the net impulse. And of course, because impulse is a vector quantity, the net impulse is a vector addition problem. Well, when I think about what that is, so that's just going to be adding together the vector j1 plus the vector j2 plus the vector j3. But in terms of those definitions, that's just an integral over some time interval of force 1 dt plus the integral of force 2 dt plus the integral of force 3 dt plus keep adding those together. And as long as I keep my time interval the same, assume that what I'm interested in is all of these forces acting over the same time interval, then of course that means that basically I can do the vector summation of the forces inside the integral. And so the net impulse I can also think of as the integral from some initial point in time to some final point in time, so again integrating over my time interval, of the net force times dt. Newton's second law, I know that the net force is equal to ma, and of course the acceleration is defined to be the derivative with respect to time of the velocity. Take my net force, use Newton's second law, then use my definition for the acceleration, I'm left with an expression where what I notice is these two dt terms, one's on top, one's on bottom, so they actually cancel out. And so what I've got is an integral where I can cancel out those two dt terms, and then if I tuck the mass back inside, we often pull it out. We've pulled it out if the mass is constant, but of course if it's constant I can put it back in just as easily as I can bring it out. And so that leaves me with a little differential of mv, and that's just the momentum. And so what I notice is when the dt's cancel, I'm left with basically the integral from some initial momentum to some final momentum of a differential element of momentum. When I integrate and evaluate at the endpoints, that just gives me delta p. So what I see here is that the net impulse is equal to the change in momentum. And so we talked about that impulse and momentum are very intimately related, and here in some sense is the fundamental relationship telling us how, that if you calculate out the net impulse acting on your object, it's going to be equal to the change in momentum of your object. So what happens when a net force acts on an object over some duration of time? Well, that net impulse acts to change the object's momentum. And so this relationship is known as the impulse momentum theorem. And so one thing to make sure is very clear is, again, I can ask you to calculate out the change in an object's momentum. So what is the change in momentum of this object? I can also ask you to calculate out what the net impulse is exerted on an object, and that's fundamentally the same problem. So I've asked you the same problem, just using two different phrasings, because those two things are equivalent using the impulse momentum theorem. Now the impulse momentum theorem should look familiar because it does look an awful lot like the work energy theorem. And so the work energy theorem told us that the net work was equal to the change in kinetic energy. The impulse momentum theorem says that the net impulse is equal to the change in momentum. And so one of the things that I'll go ahead and highlight now to sort of set up the next video is what we have seen in talking about energy. The work energy theorem is very much our fundamental way of keeping track of what's going on with energy. Now we reframe that so that there was the work energy theorem, we reframed it to talk about conservation of energy or energy balance, whichever way we choose to label it. And in the same way, what we're going to see is the impulse momentum theorem is in some sense another way to think about the fundamental idea underlying momentum. Again, we can reframe this, and what that reframing is going to do is it's going to lead us straight back to Newton's laws. We've emphasized on multiple occasions that this class basically is thinking about two problems. One of them is keeping track of energy and how it changes for a system. The other is thinking about momentum and how it changes. And so here are, again, just two ways that we can think about the two fundamental problems of this course.